And at first, we discussed the general theory for an error term. So definition. So we want to have some general distribution to express all the error terms. So definition, that we say the y is from the exponential family. So we define exponential family. If the f of y, this is the PDF, so the probability density function of y is equal to the exponential of y theta minus b theta, b of theta, divided by a of phi plus the function of y and phi. And for some parameters, theta and phi, and also some functions a and c. So here the theta is called the canonical parameter. So this is the regular parameter, and the phi is called the dispersion parameter. So a of phi is in the denominator of y, so it's kind of natural to say that this is dispersion parameter, or the scale parameter, I would say. Yeah, yeah. So for example, if we think about the exponential distribution, then the maybe, okay, so exponential distribution, then this theta in exponential distribution is actually the location, the scale parameter. So you can imagine that the phi represents some scale. And the theta is called the canonical parameter, and this is location parameter. So theta is basically here on the numerator. And you can see in the next slide, next example, why this it represents the location. Yeah, and the textbook uses this definition, but the usual definition of exponential family is a little wider. So this y theta in the exponential function is usually the t of y, a function of y, a vector of functions of y transpose times theta. And here the t of y and the theta are both vectors. So yeah. So just even if the y is the univariate distribution, still the expression on the right hand side maybe, for example, maybe y and the log of y. Then we transpose, then we multiply some theta 1 and theta 2. So this is also possible. And actually the gamma function, gamma distribution, and for example, multinomial distribution. So those distribution is the more general definition of exponential family. Okay, so here are some examples for exponential family. So first example is the normal distribution. So suppose y follows normal distribution with mean mu and the variance sigma square, then as we know, the probability density function of y is the 1 over square root of 2 pi times sigma times exponential of the negative of y minus square of y minus mu over 2 times sigma square. Okay, so then we can transform this into the same shape as the exponential family. So the exponential family, it should be the y times some parameter minus the function of parameters, then divided by some other terms. Then remaining term that should not include this parameter mu. And you can see that yes, originally that was theta, but this is the y minus mu, and minus the mu square over 2. So now you can see that the y, the canonical parameter, is considered as location parameter. Mu is location. And actually, if you expand the square of y minus mu, then the linear term of y, the coefficient is mu, so that should be location parameter. Then this is just the constant term in terms of y, and this is sigma from the denominator. Yeah, so in the definition of exponential family, that we have the theta is equal to mu, and the phi is equal to sigma square here. So we can see that the phi represents the dispersion or the scale parameter. And actually here, we define the phi is equal to sigma square, so A of phi is equal to phi. And the B of theta is equal to here, so mu is equal to theta, so that's theta square over 2. And then the remaining term is C, so C of y, C phi is the negative 1/2 times this quantity. Yeah, so now you can see that y theta is regarded as location parameter and the phi is regarded as dispersion parameter. And yes, so this is exponential family. And the example 2. And Poisson distribution. This is also in the exponential family. So exponential family is pretty wide class. So Poisson distribution is a discrete distribution. Normal is the continuous, but both are in the same family, exponential family. Okay, so what was the Poisson distribution? So the probability mass function of Poisson distribution is exponential negative mu times the mu to the power y over y factorial. So basically, this decays the pretty fast as y gets larger because we have y factorial on the denominator. And the numerator, it depends on the value of mu. Mu is less than 1, that it decays the exponentially fast to 0. Mu is positive, then actually the mu to the y's power is getting larger as y gets larger. But anyway, the y factorial that makes the entire quantity smaller. And if we put everything on the exponential part, then e to the power, okay, so mu to the y's power becomes the exponential of log mu to the y's power. So that is the exponential of y times log mu. So here, the y times log mu. So log mu is the theta in the definition of exponential family. And the phi is 1 because we don't have any denominator here for the y theta. So a of theta is 1. Okay, so a of phi is equal to 1. So no phi actually here. And the b of theta is equal to mu here, but we define the theta is equal to log of mu. So we should say that this is exponential of theta. And the remaining term is just the c of y phi, even though phi is 0. And another example, the binomial distribution. So suppose that the y follows binomial NP. The textbook uses mu, but here I use p because textbook uses the mu as the expectation of y, and here expectation of y is n times p. So the number of trials times the probability. So I put p here. And the probability mass function is the n choose y times p to the power y times 1 minus p to the power n minus y. So you can rewrite this as this. So basically the p is equal to e to the power log of p. So that term becomes exponential of y times log p. And the next term, the n minus y times log of 1 minus p. But to verify this is from exponential family, that we have to put y and everything should be included here. So we use the log p and negative 1 times log of 1 minus p. So the coefficient of y is the log of p over 1 minus p. And the remaining term is here, n times log of 1 minus p. And the remaining term is the term without p. So here, the theta is equal to log of p over 1 minus p, and the b of theta is equal to negative n log of 1 minus p. But this, the log p over 1 minus p, this is a logit function. So what is log of p? So log of 1 minus p, we can rewrite in this way because the theta is equal to log of p over 1 minus p. So that means the e to the power theta is equal to p over 1 minus p. Then 1 minus p, p theta is equal to p. So that means the p is equal to 1 over 1 plus e to the theta's power. So that means 1 minus p. So actually, the numerator should be e to the power theta. So that means 1 minus p is equal to 1 over 1 plus e to the power theta. So finally, the negative log of 1 minus p becomes log of the 1 plus exponential of theta. Then we multiply this n, so n times log of 1 plus the exponential theta. Okay, so maybe I would write that log of 1 minus p is equal to the negative 1 plus e to the power theta. Yeah. So that makes this. Yeah. And the c function, c is here. So this is just a reminder. And here again, the phi is equal to y and the a of phi is equal to 1. So actually the phi does not exist. So the binomial distribution and the Poisson distribution, we only have one parameter which dominates both the mean and also the scale. Yeah, so one remark. So we have seen the over dispersion models for binomial and Poisson regression. So sometimes we may want another parameter to adjust the variance even when the phi is equal to 1. So we define the a of phi is equal to the phi over w in such cases. So the motivation isn't really clear. So for normal case, the phi is just independent parameter from theta, so that's fine. And the binomial and the Poisson case, actually we don't have phi, so we really don't need phi. But here we just ignore phi and we introduce another parameter w. But anyway, so the idea is that just add one parameter just in case that we cannot control the variance by the original parameters.